Welcome to the Rocket Science 101. Today we are going to talk about electric rocket propulsion. Electric propulsion represents one of the most promising technologies for the future of spaceflight. Unlike chemical rockets that release energy stored in propellants, electric thrusters rely on external power sources, such as solar panels or nuclear reactors, to accelerate propellant to very high speeds. This efficiency is measured as specific impulse, which tells us how effectively the engine uses propellant. Electric thrusters achieve much higher exhaust velocities than chemical rockets, but they deliver only very low levels of thrust. That is why these engines cannot lift a rocket off Earth, but are perfect for long-duration missions in the vacuum of space. Electrothermal thrusters. The first category of electric propulsion is electrothermal propulsion. In these systems, a propellant such as hydrogen, nitrogen, or hydrazine is heated electrically. One version, the resistojet, works like an electric kettle. Electricity heats a chamber, warming the gas before it expands through a nozzle. Another, the arcjet, uses an electric arc like a controlled lightning bolt to reach much higher temperatures. But designs are relatively simple, reliable, and often used for satellite orbit adjustments, though their exhaust velocities are lower than more advanced electric thrusters. Ion thrusters. The second type is electrostatic propulsion, commonly called ion thrusters. Here, xenon gas used because its atoms are heavy and easy to ionize. Ionization means stripping electrons away, creating positively charged ions. These ions are then accelerated by strong electric fields to speeds of up to 60,000 meters per second, much faster than in chemical engines. To prevent the spacecraft from charging up like a giant battery, a neutralizer injects electrons back into the ion beam. The result is the iconic blue glow seen in missions like NASA's Dawn spacecraft, which used ion propulsion to visit multiple asteroids. Electromagnetic thrusters. Another major branch is electromagnetic propulsion, also known as magnetoplasma thrusters. These devices accelerate plasma, which is often called the fourth state of matter, a hot, electrically charged gas of ions and electrons. When electric currents flow through the plasma inside magnetic fields, the Lorentz force pushes the plasma out at very high velocities, sometimes as high as 75,000 meters per second. A widely used version is the Hall effect thruster, which creates a donut-shaped plasma and produces a steady blue ring of exhaust, powering satellites and interplanetary spacecraft today. Electric propulsion is not about raw power, it's about endurance. Even if the thrust is weaker than the weight of a sheet of paper, applied continuously for months or years, it can change a spacecraft's velocity by thousands of kilometers per hour. This cumulative effect makes electric propulsion ideal for deep space exploration. From simple resistojets and arc jets to advanced ion and plasma thrusters, these engines are already changing how humanity travels through the solar system and will be critical for future missions to Mars and beyond. Thank you for watching. See you next episode.